Hello and welcome back to Pre-Calculus, section 7.2 on systems of equations in three or with three variables. These are systems that are actually representing planes in space. Your 2x2 systems from elementary algebra were lines, so they would intersect into a single point or they would be parallel for no solution, stuff like that. Now, when we are talking about these larger systems, say a1x plus a2y plus a3z equals to some number a4, and then b1x plus b2y plus b3z equals to b4, and c1x plus c2y plus c3z equals to c4. These, sometimes we put this brace to kind of put these equations together, and we say that these three equations create a system of three equations and three unknowns, and that gives us actually intersection of three planes. Now, what is a plane? Plane is just a flat surface like your wall and the ceiling and the surface of the desk, surface of the screen, if it's not curved, and so on. So whatever flat surface you're looking at, it can be expressed as a plane. Now, that is the part of Calc 3 to learn about the equation of the plane and the calculus of it and all of that stuff. Now, we are only learning what happens when you intersect those planes. So now if you take a look at the corner of your room, you have a plane represented by the ceiling. Let's say your ceiling is 8 feet tall. So you will have a z equals 8 as your ceiling. And then you will have your x and y walls, right? And one equation would be x equals a number, the other one would be y equals a number, because those planes are all perpendicular and nicely oriented. But you can have planes that are angled, right? What I want you to take a look real quick at the corner of your room and understand that the one wall, which is one plane, the other wall is the other plane, and the ceiling is another plane, they all meet at that corner point, right? Where the spider usually likes to make a little web. And in that corner is the corner point of intersection of all three planes. But if you take a look at the plane, which is your floor, and the plane, which is your ceiling, those two planes never intersect, right? Which means that the systems containing those two planes would not have a solution because the planes never intersect. So we have technically the same deal that we had with lines when the two parallel lines never intersect, creating the xy intersection point, which is the solution. So two parallel lines have no solution. If some of these planes end up being parallel, well, they don't have the solution to the system either. So you can also run into a no solution systems when you have 3 by 3. And you can also run into infinitely many solutions when two planes turn out to be the same plane, and that intersects with another plane, and the intersection between two planes is a line. Now that's that line that connects one of your walls and the ceiling, and that infinite line going, let's say, left and right, would be the line that would have infinitely many solutions. But that's, as I said, if two planes were the same plane, and then the third plane is different plane, so those two planes intersected with the third plane would just create a line which creates infinitely many solutions. Now, in our calculations, it is very easy to distinguish between three types of the solutions, because with calculation, without going into geometry of the whole thing, which mainly, as I said, is in Calc 3, three types of the solution is number one, x, y, z. You get numbers for each one of these, x, y, and z, when you're done with your calculations. And because you have numbers, for all of these, that would be your one unique solution, and you are done. Now, you can also have a no solution, and that happens when you get some nonsense like 7 equals to 3 or something like that, right? You know that 7 is not equal to 3, but the calculation gave you 7 equals to 3. So in that case, there is no solution. And the last case with the infinitely many solution is when you get a true statement like 7 equals to 7. Then you know that there are infinitely many solutions for that particular set. So you can either solve them and get x, y, and z to be the numbers, and then for no solution you will get what I call mathematical nonsense, right? It's a untrue statement. And then for infinitely many solution you do get the true statement. It doesn't have to be 7 equals to 7. It could be 13 equals 13 and so on. Just two same numbers. So we can upgrade now these examples into a not equal to b and a equals to a, right? So you would actually get the same number on both sides. Now, throughout the years, I taught this, but probably most interesting when I just started tutoring, I ran into a lot of students who really had a lot of trouble to solve this because they were just disorganized and lazy to copy equations and to keep things organized. So they would be running in circles and, you know, kill the variable in one set of equations, then go into the another and try something, and it just run in circles, and then they would be frustrated and punching holes in a wall because they couldn't solve these systems. It's very easy to actually get lost in all of this if you are disorganized. So I'm going to propose a very systematic way to solve these in the same amount of steps every time, or less if the systems are in your favor. So let's take a look at that. Just going to steal example from the homework real quick. So x plus 4y minus z equals to 20. 3x plus 2y plus z equals to 8. And 2x minus 3y plus 2z equals to negative 16. First order of business is get used to crossing your z's, because is that 2z or is that 22? It's definitely not going to be zz, we know that, but it could be 22 or it could be 2z. Now it's definitely 2z. So get in habit of crossing your z's if it's not your habit so far, and it will help you greatly. Right? Now, after that, go to your system and pick a variable that you want to eliminate. In all honesty, it could be any variable, so you can always pick the same variable going to a system. But also, right, we could pick in a smart way so that we speed up the process a little bit, and in that time, right, to also work with smaller numbers. So let's say you pick the worst one of all, y. Well, you have to combine 4 with a 2 and 4 with a 3, or 2 with a 3, right? Where if you pick a z's, 2 of them are already set for you to add those two equations, and z's are gone. So you just have to work with the third equation to eliminate z, you just need to change one equation. But if you want to eliminate y, you have to change all three equations. So this type of analysis will be there with practice. So if you obviously do only 2 or 3 homework exercises, you will not have that as a habit. You will be possibly, wasting some time to solve the problems. But if you do a lot of problems and you know what to look for in a system, right? Obviously, you practice more, you know more, and everything will work faster. So what I'm going to do is I'm going to take the first and the second equation. I'll use red to put those together. And when I add these two equations, z is gone. On the other side, I'm going to use in blue, I'm going to multiply top equation by 2, which will give me negative 2z, and add that to the third equation, which would kill z in that pair as well. So I'm actually using the first equation twice, but as you can see, the first equation now is multiplied by 2, so that I can combine it with the third equation. Now, third equation, as you can see, is written as is, because I haven't done anything to that equation, and I will be adding those equations. So when you add your red pair and your blue pair, the resulting equations will not have z in them because you eliminated z from both pairs, and you will be back in your basic algebra, elementary algebra system, 2 equations, 2 unknowns. So going to the red system, we have 4x plus 6y, z's are gone, equals to 28. And going to the blue system, we have 4x plus 5y is equal to 24. So now, when we put these equations together, we created a system from elementary algebra, and all I need to do is to subtract these two equations. That's it, because that would kill x's immediately. So I have 1y is equal to 4. Done. Now go back, figure out x, go back, figure out z. We have two equations to pick that connect y to x. So we can say 4x plus 6 times 4 is equal to 28. 4x is equal to 28 minus 24. X equals to 1, right? Because 4x equals 4. Divide both sides by 4. And we get this one. Now just go into any of the equations on top, and I'll use the second one because it has smallest numbers. And z is already isolated, it's alone, right? So we have 3x plus 2y. So 3x plus 2y plus z equals to 8. That is, y is 4. There we go. So that's 3 plus 8 plus z equals 8. So z is negative 3, right? 8 cancels 8. 3 goes to the negative side. To the other side becomes negative. That's what I mean. And now you present 1, comma, 4, comma, negative 3. This is a three-dimensional point, right, in space. So x, y, z, you always put x first, then y, then z. And the problem is solved. Now, if you care, right, you can check, make sure that it's good. And for that, you plug all of these variables and make sure they're equal to 20, and then 8, and then negative 16. So x plus 4y minus z, that's going to plus 3, equals to 20. Okay, that one is good. Then 3x plus 2y plus z, that's minus 3, is equal to 8. That's good as well. And then 2x minus 3y plus 2z, that's a minus 6. And that's going to be negative 16. Good. They all worked out. The solution worked out in all three equations, which means that this is the solution to the system. Now remember, I said this for basic 2x2 systems in algebra. Same thing follows here. If one equation doesn't work and the other two work with your solution, you have the wrong solution. So check the check first and then go and redo the problem. Chances are you're not going to find it where it's wrong. It's because a lot of calculations. I would suggest you start the problem from scratch, and then if you get the same answer, do it again and again, right? Or again, check your check, right? But with the 3x3 system, you can have two equations working and then third one fail, right? Which means that your solution is definitely wrong. So be very careful about that stuff. And believe it or not, that's it. So now we're just going to practice other examples. And as I said, always think about what is the fastest way, most convenient way to solve the system. Sometimes you will have a system with a variable missing, which means just use the other two equations to kill the same variable. So in this case, x plus 3y, this is problem 14, right? So x plus 3y plus 5z is equal to 20. And then y minus 4z is equal to negative 16. And then 3x minus 2y plus 9z is equal to 36. So x is already missing over here. Great. All I need to do is to multiply top equation by 3 and then combine first and third equation by subtracting them to kill that x again. So the first equation times 3 is 3x plus 9y plus 15z equals to 60. Usually, when you make a mistake, you forget to multiply this number, right? This is usually, not always, but usually, that's where the mistakes are. For whatever reason, you do not multiply by whatever number you have, and obviously that will make everything to be off. So for this, right, we have multiplication for this one, and then we just copy the third equation, 36, and now we just subtract the two equations because 3x minus 3x would be 0. So 9y minus 2y is positive 11y. 15 minus 9 is plus 6z. And 60 minus 34 is positive 24. So two equations I'm working with are y minus 4z equals negative 16. That's the equation that did not have x to begin with. And our new equation that we have. Now, if you are dead set on substitution, elimination, you are going to work with large numbers now because you would have to multiply top by 11 and then subtract, or negative 11. And that's not fun. Anytime you have single variable, use the substitution method immediately. This is 4z plus 16. This way, you don't have to multiply by 11 or multiply top by 6 and bottom by 4. I mean, you can, right? You have the calculator. You can be brain dead and still do it. But if you are looking for a somewhat easier ways to go about it and avoid the calculator, then substitution, right? Anytime you have the variable, any four of these, to have a coefficient of 1, you can immediately jump with substitution. So our bottom problem now becomes 11. In a parenthesis, I'm going to have 4z plus 16. And then plus 6z equals to 24. And now, if I hide everything, all you have is equation that has one variable, which is variable z. That's 44z plus 176 plus 6z equals to 24. 44z plus 6z is 50z. And when you subtract this on the other side, you get negative 150 because my 76. Oh, wait. That's 152. Did I miss anything? 16, 16. Yeah, 176. That's good. I mean, we can get fractions, but it's so close to 3 that I really. Okay, let's see. Oh no, that's good. I thought I did the subtraction wrong, but I didn't. 3 minus 3 is 0. 9 minus 2 is 11. 15 minus 9 is 6. 60 minus 36 is 24. Then we copy equation, and that's negative 16. Aha, this sign is wrong. It's negative 16. This sign over here supposed to be negative because I'm moving 4z to the other side. The sign of 16 has to stay. Okay, there we go. So that's minus 16 over here. And because that is a minus 16, then this is going to be negative 176. Oh, and that makes this 200. Okay, there we go. Z equals to 4. We can get fractions, okay? But it was so close to 3, and now when I found the mistake, it turns out that actually it's 4. Okay, such is life. Now we have equation for y. So y is equal to 4 times 4 minus 16. That's 0. Cool. So now we have that z is 4 and y is 0. Those are the two that we have so far. And all I need to go is to find an equation to calculate x. Now, first equation is perfect because x is single already. So x is equal to 20 minus 3 times y minus 5 times z. 3 times y minus 5 times z. That's another 0. 20 minus 20. So the solution seems to be 0, 0, 4. Now, when you have a solution simple like this, 0, 0, 4, you can just go and check that solution just by looking at the equations. Because if x is equal to 0, all of these are 0, all of y's are 0. So technically, 5 times 4 is 20. Good. Negative 4 times 4 is negative 16. Good. 9 times 4 is 36. Good. So you can check that way when solution is this easy, which is great. Can we make this difficult? No. Can we make it annoying? Yes, right? So here is one problem for you to try. I'm going to mute myself for some time. You try this, and then we're going to get together and take a look at the solution. Now, when you get the solution, check it, right? Because you don't need anyone to tell you it's right or wrong. I mean, I'm not going to know until I do the problem whether your solution is right or wrong. But what you can do is you can check the solution you got, and then you don't have to ask. So here we go. 7z minus 3 is equal to 2 times x minus 3y. 5y plus 3z minus 7 equals to 4x. And finally, 4 plus 5z is equal to 3 2x minus y. As you can see, it's not really given in that xyz form, so you have to massage it first right into that form and then solve it. So try this for a couple of moments, and we'll get together to solve this. Go. Any luck? Or it's too early to ask?
Hey, Professor,
Yes.
can we start going over it to see if I'm on the right track of solving it?
Okay. Did you get any of the variables yet, or you
No,
got stuck?
I got stuck for sure.
All right. Let's take a look. That's fine. I mean, first thing is to get all of these multiplied so that we can sort them out because we need x and then y and then z. So we
Mm-hmm.
have 7z minus 3 equals to 2x minus 6y.
Mm-hmm.
The next one is 5y plus 3z. Oh, there's nothing here for now. And then 4 plus 5z multiply out into 6x minus 3y. There we go. So now move everything to the side. And you can actually, we're going to say 2x minus 6y and then minus 7z equals to negative 3. So we keep this one, keep this one, keep this one, and just move one of them. Now, which side of the equation you write, it doesn't matter. Same thing goes here. We're going to keep 4x in place, move 5y, move 3z, and keep negative 7 in place. And the last equation, keep 6x, keep 3y, move z, and keep 4 because it was on the opposite side. So once we have this, this is the system that looks exactly the same as the ones that we covered so far. So now we pick a variable to eliminate. The best one is x, because if you multiply top equation by 2, you can eliminate x with a 4x. And if you multiply it by 3, you can eliminate with a 6x. So, multiplying top equation by 2 to create my red pair. 4x minus 12y minus 14z equals to negative 6. And copying second equation as is for the red pair. I'm going to subtract these equations. Then multiplying top equation by 3 so that I can have 6x and then eliminate with the third equation. So 6 times that is 18y minus 21z equals to negative 9. And the bottom is, we just copy the third equation because it is, we haven't done anything to it. We'll just leave it there. And again, we subtract these equations because that will eliminate x's. All right, let's go. 4 minus 4, that's gone. Minus 12 minus 5 is plus 5, so that's negative 7y. 14 minus 3, that's going to be negative 11z. And then 6 minus 7, minus 6 minus 7 is positive 1. On the blue side, subtraction, 6 minus 6 is 0. 18 minus 3 is minus 15y. 21 minus 5 is negative 16z. And negative 9 minus 4 is negative 13. Oh, look at these equations. Nothing matches here. This is terrible. I hope that, well, we'll see. Hope that the numbers that we get, um, well, we'll see. Maybe they are fractions, maybe they're whole. I don't know. It doesn't look promising. Now, when you have so many negative signs, if you want to, you can always multiply by negative 1, right? And all of the signs will change across, and then you don't have to worry about negatives. So you will only have negative 1 on this side, but everything else becomes, as you can see, positive because we had so many negatives. Like everything was negative except that one. Well, cool. There we are. Now, we don't have a single for substitution. All of the numbers are large. And we are going to multiply here by 15 and here by 7. That's the best we can do. The other option is to multiply by 11 and 16, which is worse. And trying to do substitution with immediately going to fractions. So this is our best option. All right, so 15 times 7, that's 70 and 35, 95y, plus 165z equals to negative 15. And then times 7 is again 95y, plus 70 and 42, 112, z equals to 70, 91. All right. So now when we subtract these equations, y's are gone. 165 minus 112 is 53z. That doesn't look good. 53z. And when I subtract the other equations, these numbers actually add. And they add.
Professor, I have a question.
Mhm.
Isn't 7 times 15 105?
Is it?
I was using a calculator and yeah.
Oh yeah, because it's 70 plus 35. It is 105. Yeah. Okay, but in anyway, that cancels. So it does not, luckily, it doesn't wreck our calculation. I hope that the other numbers are good. The other numbers should be good. They look good. Ooh, 106. Yes. 106, that's half. Z equals to negative 2. Okay, I'm happy. It looks like we're good. So Z is negative 2. And it really didn't look good when I got 53 here. But the other worked out to be 106. Nice. Okay, so now we have our equation for y. We can use 7y plus 11 times negative 2 equals negative 1. And from there we can get our y. This is going to be negative 1 plus 22. Wow, look at that. Y is 3. Nice. And now for x, use any equation from the beginning of the system. We can use the first, second, third, doesn't matter. First, because we're just going to divide by 2. So 2x minus 6y, 2x minus 6y minus 7z equals negative 3. And 2x is equal to negative 3 plus 6 times y, that's 18, plus, oh, it's going to be a minus because it's negative and negative, and then change the sign, change the side. So we have 2x equals to 1. X equals a half. Okay, we can live with this. So half 3 negative 2. And now, since we got this 1/2 from the first equation, we know that these numbers will work in the first equation because we already had all of these numbers in the first equation. So we would need to check the second and third equation and make sure that the numbers work in both of those equations. Or, even better, copy the original system and place these values in the original system to see if everything works. So 7z minus 3 needs to be the same as 2 times x, which is a half, minus 3 times y, which is 3. So these two have to be the same. I have negative 14 minus 3 should be the same as when I distribute, well, 2 times 1 half minus 9 first. On the left-hand side, I have negative 17. And on the right-hand side, when I multiply by 2, I get 1 minus 18, which is negative 17. Okay, so first equation works great, which it should. We got these numbers from the first equation. It's the second and the third equation that we should worry about. 5 times y, it's 5 times 3, plus 3 times z, which is negative 2, minus 7 should be 4 times 1 half. That's 15 minus 6 minus 7 should be equal to 2. Yep, 15 minus 13 is 2. Good. So we are good on the second equation. And now third equation, 4 plus 5z should be the same as 3 times 2 times 1 half minus 3 minus y. So that's 4 minus 10 is supposed to be equal to 3 times 1 minus 3. 4 minus 10 is negative 6. Should be 3 times negative 2. Negative 6 equals negative 6. It worked in all three equations, which means this is definitely our solution. And yay. Those are the 3 by 3 systems. And let me point out one more time the secret to solve them. If you get something annoying, multiply everything and move it left and right and so on, so that you can get the system that you used to. Here are all the x's, all the y's, all the z's, everything lined up properly, equal to a number on the other side. So we are looking to eliminate one. You're creating two pairs of equations, and you are looking to eliminate the same variable in each pair. That's your job. So I decided to remove x's because they are the easiest, because 2x goes into 4x and 2x goes into 6x. See, 6 with the y's, you have a 6 and a 5, and they are not really friendly. 6 and 3 are friendly, but 5 is not friendly with 3 or 6. And the same thing happens, the z is the worst, because nothing works with anything. You have a 7 and a 3, and a 7 and a 5, and 3 and a 5. So that works. None of the z's work nicely with, coefficients of z work nicely with other coefficients. So that's the reason why we picked x. And the first two, right, for the red, and the first and the third for the blue, because 2x times 2 gives you 4x, and 2x times 3 gives you 6x. So create the two sets, eliminate the same variable, and then go on with the 2 by 2 algebra system to eliminate the rest. And just keep in mind that if you are already missing one of the variables or more, you can miss more than one, you can just work on the other two equations. So as you can see, there's no blue set here because the second equation was already missing an x. So I just used the first and third equation to eliminate x. And we immediately got into the two equations and two unknowns on a second shot. It is very systematic, and as you practice these problems, you should pick it up. Any questions, concerns? All right. Well, we'll see you in the next lecture.